Excellent. Thank you very much for the introduction. I'm Niels Bultink from the company QBlox. I'm very happy to be here and represent our technology. I'm here to talk about the coherent and massively parallel shift of the quantum control paradigm. So, as is very common in many talks today here, it's clear what we need to do as a field. We need to improve on quantum computers on many aspects. So it's on the scalability axis where we need to go to much higher qubit count, and at the same time we need to go to much lower error rates and also correct errors. So in all parts of the stack, this will mean revolutions have to be built. Our revolution is in the control stack. It's the interface between algorithms on the left side and with the quantum processors on the bottom side. And that is what we are doing with a laser focus. So our company spun off from QTech in Delft in 2018, where we spun out with a lot of intellectual property around this control technology, because it has been already a tradition of many years to build high-end equipment. We find ourselves in a very vibrant ecosystem with many partners, small companies, spin-outs, blue forces on campus, but also large IT firms like Intel and Microsoft that create a very vibrant and collaborative spirit. Our company QBlox is so far supporting 25 labs around the world on 4 continents. And we're doing that now with a team of slightly over 20 people. And we are growing very fast because there's a very good demand for our solutions. So at the moment, I'd like to summarize the state of our art as we can control 100 quantum bits from just 1 meter of electronics. This is the kind of a metric we introduced to talk about scalability. And this is best exemplified by providing some context. So what does a control stack look like right now around the world? I think these pictures here are very recognizable, in this case from 2 major labs in 2016 and 2019, doing major breakthroughs. But the control stacks they use for it are actually not very scalable. They're quite bulky, with very high cost per qubit. They're very error prone, quite noisy, and quite slow to operate. So there's a lot of need to improve on these systems. Our answer to that is these type of stacks. We call them fully integrated quantum control stacks, meaning that all equipment needed for controlling the quantum device is included in a single package. So it's, in this talk, I will go through 4 aspects. The first being fully integrated. The second is about analog excellence. The third is about fast and open workflow. It's more about the software. And lastly, we will talk about the power of distributed processing. So on the hardware, about fully integratedness. Controlling, say, 20 transmon qubits requires really a myriad of instruments. So here on this slide, you see the combination of devices. You need readout analyzers, local oscillators to create microwave tones. You need many AWGs. You need a lot of IQ mixers, spectrum analyzers, a central controller to tie them all together, and about 120 wires to make this all work as one system. And our alternative solution to that is standing here right next to me. This is called the cluster. And this has all of these instruments combined into one modular package. And so this modular approach does not allow just to do this for a 20 qubit setup, but it also allows starting small and gradually building up a setup towards a larger and larger application. So to give 2 examples in superconducting circuits and quantum dots, here on this slide is an example how you build a 4 transmon control system with just 5 modules. So it's actually just occupying 20% of this device to do all of the tasks: readout, control, 2 qubit gates, single qubit gates, everything is in there. Similarly, for spins, we provide solutions as well using the same modules but in a slightly different configuration. Here, looking at a 5-dot setup that we built for one of our customers, providing also all of the control and readout solutions from just 5 modules for these 5 spin qubits. So to dive a bit more into the details of this integrated hardware, I here show you one of our latest modules. This is a direct microwave driving module that can pulse directly at microwave frequencies between 2 and 18 gigahertz. So in this case, on the left side, you see the digital architecture. So it has a sequence processor that determines all the operations as a function of time. And it does it by triggering waveforms from a waveform memory, which is going from digital to analog in the middle here. And in the same module, those pulses are directly up-converted towards the microwave regime. So in this module, there are 2 onboard local oscillators that can be set to between 2 and 18 gigahertz to directly create these outputs. This does not only make it into a more compact and easier solution, it also provides a lot of opportunities to work on the signal quality. So with this solution, you can reach really high signal purities. This is exemplified here by the spurious-free dynamic range. So we can create pulses with spurs more than 55 dB below the output power. And this signal quality is also maintained when doing multiplexed signal generation with these outputs. So this is one example of the analog excellence that we reach with these solutions. Another very important one, and perhaps crucial for improving quantum processors, is in the ability to improve 2-qubit gates. 2-qubit gates are in many platforms, dots, superconducting circuits, limited by 1/f noise in the AWGs. So what we did is we have been very carefully making a new output stage that is very low noise. And here we reach very low noise levels that, to our understanding, is by far the lowest available on the market right now. So it can really help to push gate fidelities towards the next milestones. This is about reaching a high gate fidelity, but what is also important in large systems is that fidelity can stay up for a long time, because large systems spend a lot of time in recalibrations. So for that, stability is paramount. Stability is often a not even quoted or specified number in this type of equipment because it's not really looked after. What we did is we have created a very stable output that is at the level of 5 parts per million per Kelvin. So to give you some context, this is a number that is typically only achieved in battery-powered DC sources. But we here reach this type of stability in a fast pulsing apparatus. And this minimizes the need for calibrations and overall gives a much higher gate fidelity. So now let's dive a little bit into the digital architecture to understand what workflows can be done with this. So in the digital side, everything starts at the heart of the sequence processor. The sequence processor is our own built processor that we embed in an FPGA. And this Q1 processor allows for various things to sequence operations and to modify operations in real time. So in a sense, it triggers pulses from a waveform memory as a function of time. But we add a few tricks to make much more efficient use of this waveform memory. For instance, we can do multiplexing by using multiple sequence processors at the same time. And we can use real-time adaptable parameters in the digital signal chains, the gains, offsets, and the phases of the modulation. And this allows to make much more efficient use of the memory. As an example, you can do in this architecture arbitrary single qubit gates from just one pulse pair, making much more efficient use of the memory. Another example is in using this architecture for calibration purposes. So many calibration routines, you are varying some parameter. So by doing this parameterization of operations in real time on the hardware, you can really run over large numbers of parameters in just single experimental runs. And in this example here, this is a two-dimensional scan. The total measurement time is reduced from about 1.5 hours towards just a few seconds by employing all these fancy tricks. So how to make use of this as a user? We have various levels of APIs that we provide to access this sequence processor architecture. The more high-power user use the system directly at the level of assembly. And we fully document this level. So people can use their own compilers to compile the assembly that runs on these devices. Alternatively, smaller labs want to have a more convenient interface. That is what we built with our partners at Orange Quantum Systems. We create this package called Quantify that does, amongst many things, it creates a very convenient scheduler to make use of our hardware. So this starts at providing a high-level intuitive programming language to schedule operations. These can be COSM-like operations, or they can also be arbitrary pulses, and it can be interleaved with classical operations. Then this is also converted into a visualization backend, so that you can, before uploading, before starting the measurement, you can see exactly what the output is at all the channels of the system. So now I've gone through most things of the system. I'd like to talk a little bit about the power of distributed sequencing. In my opinion, distributed sequencing is the only way forward in scalable quantum computers. And it's unique that we can already employ this type of architecture in this system. So to make you understand and make you appreciate the power of this architecture, I'd like to talk a little bit about the alternative. That's the centralized architecture or single chip architecture. This is what most arbitrary flow type of experiments, or I think all arbitrary flow experiments have been like, where people employ a single chip, an FPGA, or perhaps you could also do it alternatively with an ASIC, that doesn't really matter, where you use one sequence processor to control all the channels, all the qubits in the system in one go. And this is a very convenient and simple architecture, but it's also good to realize its limitations. And the limitation is in the bottleneck here. All the information to control the quantum device has to come from one chip. And the bottleneck is in between the chip and the analog data converters. And this is just already an I/O bottleneck. So with one chip, even the most high power FPGAs or ASICs, you will roughly have 500 I/O pins. And this is just enough if you would really push it to the max to drive around 32 DACs and ADCs. And this directly limits the amount of qubits that you can control with this type of architecture to about 8, but actually more realistic is 5. So we already moved away from this simple architecture a few years ago towards a distributed sequencing architecture. So what is it? It means that there's not just one sequence processor that takes care of the experimental routines. There are many sequence processors in all of these modules that run at the same time in a harmonized fashion. And it is very powerful, but it's at the same time hard to make this work very well. And what you need to do to make this work is you need to do two things. These processors need to work harmonized, which means they need to start exactly at the same time, down to the picosecond. And the second thing is you need to be able to distribute measurement outcomes during the quantum algorithm. And that is what we do using a shared memory. And the big upside, if you have this working, is that it completely takes away many of the bottlenecks in the system. So with this architecture, fundamentally, you can easily scale this architecture towards tens of thousands of qubits. We're not there yet, but we have already set down the architecture that allows scaling this towards these numbers. So what do we have? We already have these two protocols for synchronizing the sequence processors and for sharing information in place at the level of this single cluster, where we do synchronization with a unique protocol called sync. That is a patented protocol that makes sure that all the sequence processors always start exactly at the same time, only being limited by the jitter, by the clock jitter, so it means femtoseconds. No issues with indeterministic timing. And this protocol also already works at the many instrument level. The second protocol is about sharing information, and we do this with a protocol called link. And this makes use of our proprietary backplane architecture that has a lot of digital I/O to make the sharing of data work at a fast way. So this creates this package, this cluster, that is now used around the world for experiments up to 20 qubits, and in some cases already larger systems where we use multiple devices that are synchronized. The next steps for us are in scaling this architecture up further. to go from a single cluster to multi-cluster architectures where we can maintain this type of feedback sequences. We do this in a large funded EU program with many supporting partners around the world. Second, we're using the protocols that I've just described to also build networking applications, because we don't just want to stop at quantum computing, we also want to support the next milestones in quantum internet. Specifically, we are connecting a few high-end universities in Innsbruck, Delft, and Barcelona with various different platforms, trapped ions, MV centers, and rare earth ions in one big European network. And for us, there's a very important task in this mega project, meaning we have to provide the control layer. And this control layer is going to make use of exactly the same protocols that we have implemented on a local scale, but then in a largely distributed fashion. So it means that we have to do synchronization not within a few meters, we have to do the synchronization at many kilometers distance. Second, we are going to be doing low latency data flows in this system, where we employ the same type of shared memory architecture, but then at a distributed at a much larger distance. So with this, I'd like to complete this talk. I've tried to inspire you with the control for the quantum future, and I've gone through 4 topics: a fully integrated stack, analog excellence, fast and open workflow, and the power of distributed processing. Do you need control solutions, or are you looking for strategic partners? Please reach out to us. We are here on the floor, of course, but you're also happy to connect via email or otherwise. With this, I'd like to thank you for your attention and open the floor for questions.
Thank you, Niels. We have time for one question.
Yes. Okay. Any questions? No questions? Thanks a lot. Oh, there's a question. Yes, sir.
What kind of lasers did you use to generate photons?
Sorry? Lasers. So it's good to mention that in the project, we are not providing the lasers ourselves. In this big consortium, there are also optical partners who work on laser technology. I can talk about it with you later after the session.
All right, thank you so much.
Thank you.